Hello, everyone. Welcome to today's webinar. My name is Terry Erzman. I'm the Vice President of Marketing for Citus Data. Before we get started, can you please raise your hand in the GoToWebinar control panel if you can hear me? Just want to do a short sound check. Very good. See lots of raised hands. Thank you, everyone. If you have any questions during today's session, please enter them in the questions panel in the GoToWebinar control panel, and we will answer as many as we can at the end of the presentation. Today's presentation is being recorded, and you will be sent a link to the slides and the recording within the next 24 hours. With that, I'd like to introduce our presenter for today, Marco Sloat, who is presenting real-time analytics with Postgres. Marco?
Thanks, Terry. Hi, everyone. I'm Marco. I'm a software engineer at Citus Data. And we'll talk about real-time analytics with Postgres today. So this webinar it's partly based on a tutorial we did a few weeks ago at PGConf Silicon Valley. We had some of the examples that are in the slides. There you can actually find files for that in the GitHub repository on this slide. So citusdata/pgconfsv-tutorial. So if during the webinar or after the webinar you want to try out some of the examples, you can find them in there. So the use case that we're going to discuss today is how to build an interactive analytical dashboard for real-time data. So a stream of data, stream of events is coming in, and we want to have, let's say, graphs or statistics about this data that pretty much gets updated instantly. And this is actually a very hard problem, as it turns out. So we'll look at a few different approaches and like the problems with those approaches, and then working towards something that does work, which is kind of incrementally updated aggregates or materialized views, you might call them. And then finally, we'll have some notes on how you could, if you set this up in PostgreSQL on a single node, how you could scale that out to multiple nodes. So the problem with real-time analytics is I have this big stream of real-time events data. Could be coming from servers, people clicking on things as an event, or sensors reporting back measurements or devices. Which is kind of time series data in large volumes. It could also be high volume transactional data like bookings on a hotel booking website. Lots of bookings coming in, some bookings being canceled. And you want to build a dashboard that gives you kind of real-time insight into that data by showing graphs of how many events are happening. And you can even think of like certain cases where you want this to be very, very fast, as real-time as possible. Like if you have a certain spike in your traffic that might bring down your system, you want to know that, rather within 1 second than within 1 hour. So there are many cases where you really need, real-time analytics. But then actually computing those statistics, computing aggregates over large data sets is quite expensive computationally. And, well, what you can often do if you have something that's expensive, then you do it once and you cache the results. But in this case, because we have this real-time stream of data, we continuously need to update them. So caching is not so effective anymore. So the use case we're going to look at is that of an analytical dashboard. And in particular, we're going to look at the GitHub Events dashboard, which has a number of charts on various things like traffic to a particular repository or the number of commits and other statistics. And so you can see at the bottom it shows the number of commits that were done on a repository in the last 7 days, and at the top you see a breakdown per week. This is also quite common in these types of dashboards, that you have different granularities of time, and often the coarser granularities go back a very long period, and then the daily granularity only goes back 1 week. And what's interesting, of course, is that you can actually extract the weekly information just by adding up all the daily information. Now, this particular use case probably doesn't need to be very real time, and actually I think on GitHub it is not, but we're using this because the data is publicly available. So a typical data flow for a analytical dashboard is, well, on one hand you have some source of events, so these are your servers or your sensors. You need to collect that data somehow, you need to store it somewhere, then you need to compute the aggregates, and then the dashboard needs to retrieve those aggregates. And an architecture you might see somewhere is, well, Kafka is a system for collecting data. I mean, this is just one very specific example, actually. But very often people actually store data in HDFS. Not so much because they have so much data that it doesn't fit on a single node, but actually because computing the aggregates is so computationally expensive that you kind of need a cluster for it. And then people use Spark to actually write the jobs that compute the aggregates on the raw data, using the raw data, and then that the results of that computation will be stored in some other database, maybe Cassandra or MongoDB. So these are just, lookups at this point. So the dashboard then talks to the database to do these lookups. So these architectures, and there's different variables here, but can be quite complicated with large-scale systems that need to be operated and maintained. Lots of different systems as well. But actually we'll show that you can do most of this to a fairly large scale just in regular Postgres and replace most of that architecture with Postgres. So the data we'll use in the examples is coming from the GitHub archive. So whenever a user initiates an event on GitHub or from outside GitHub by doing, for example, a git push or following a repository or commenting on something, the GitHub publishes this event in a log file. And these log files contain about 20 different event types, and each line in the log is basically a JSON object representing that event. And there are about 600,000 events per day, which amounts to about 1.6 gigabyte per day. So over the course of a year, this is a fairly large amount of data. So the format of the GitHub Events data is pure JSON objects. Now, it's not super practical to put those in basically one JSON column in a table. So for the purpose of this example, we're going to pull them apart a bit. If you look at the JSON objects, they all have actually the same fields, which is something like the GitHub ID and the type and the timestamp at which the event occurred, and then the user, the repository, organization, and then payload, which contains details of the event. So we actually wrote a tool that extracts this information from the JSON object and then can load it into this data table and make it a bit more practical to use. And so this table is going to contain a large amount of data. Like all the raw data from GitHub is going to go in here, so it's going to build up to 1.6 gigabytes a day. Now, if you go into the repository, you will actually also find a script that makes that conversion. So there's going to be a SQL file for creating the table, and there's also going to be a script that downloads directly from the GitHub archive and stages that data into the table. And it'll output some numbers of how many rows per second it's ingesting at. And these are actually separate processes. So it's actually doing 1,500 rows per second per core here. So if there's 4 cores, about 6,000 rows per second. So that's a fairly large ingestion rate that we need to support. Now, let's say we took an example where we loaded all of January into this table and then ran a query of, well, what if you just want to know the number of events by type across all that data for 1 month? And if you run such a query on Postgres, it might take a while. In this case, it takes about 25 seconds. And that's actually with everything in memory. If it's reading from disk, it could actually take quite a bit longer. So if you're, well, in the use case of having a user clicking things in a dashboard, no user is going to wait that long. So this is clearly not good enough. So we need to do something smarter. So one feature native to Postgres is materialized views. Materialized views are essentially just putting the query results in a read-only table. And if you do that, you can just query the query results basically. So the materialized view might contain data for all dates, and then or aggregates for all dates, and then your queries might only look at a particular date range. But those queries will likely be pretty fast. And you can also create indexes on a materialized views. And the problem with the materialized view is that you can't really do incremental computation, and I'll show what that means. And the way you set up a materialized view is you run this create materialized view with the name and then the query, which is something like select date and count from data and then group by date. So that you get the number of events for every day. And then sometime later, if you've added some new data, you can refresh materialized view, and you always want to add concurrently. If you don't add concurrently, this command will take a lock on the table and you can't do writes. So make sure you always add concurrently if you refresh your materialized view. So our setup then is that we have some source of events. Those events get appended to the data table, and then whenever we get new data, we refresh, and then we have this aggregation, which contains, in this case, just the number of events per day. So for now, we'll do very simple examples. And then the dashboard on this end can make queries like select star from this view, where the date is between, let's say, the last 7 days, and order by date, because I want to make a graph. And this query is blazingly fast. Just on a local connection, it'll finish in under a millisecond. So that's great. Our queries are nice and fast. So when we create the view, this would be a command that you could use to create a view that groups by date. So gives me the number of events for every day of the month of January in this case. And that takes about a minute to generate on a month of data. Of course, if it's a year of data, this takes more than 10 minutes. And then the queries are pretty fast, even if I query all the data, because it's just going to be 31 rows, basically, so it's very small. Okay, so that's great. So what about refreshing? Now, if I create a materialized view, you want to make sure always to create a unique index, and this is kind of a requirement that Postgres has to be able to use concurrent refresh, and you want to do concurrent refresh, don't do non-concurrent refresh. So make sure you create a unique index on the key such that you can do refresh materialized view concurrently. Now, what this will do is Postgres will kind of recalculate the entire table, and so we'll have to go through all the source data again and do the computations. And so in this case, this takes 50 seconds. And so that essentially means that by the time the materialized view is updated, we're already quite far behind. It's not really real time. But this could work for many applications. Like if you don't need things to get updated in a few seconds or a few minutes, materialized view can work well. Also, if you don't have a super large amount of data where building the view would just take days. So if you have a moderate amount of data and it's okay to just do periodic background refreshes rather than having actually real-time data, then materialized views can actually work quite well. But if you have large data or high rate of ingestion, or you need near real-time visibility into your data, then materialized views are probably not an option. So let's try to do something different. Well, essentially, a materialized view is not so different from just putting query results into a table. And if we do that, if we put it into an actual table, we could also just update that table every time something is added to the data table. So every time a GitHub event happens, we can load this. We can do +1 on a particular date in the daily counts table. So then, well, the performance of a query on this table or on a view are going to be pretty similar. So for the dashboard, it's still going to be very fast. So let's see how to actually set this up. So first, we'll need to create this cache table, which is just going to have, in this case, 2 columns, a date and a value, which is the number of events for that day. You could populate it with all the data that is already in the database using a query like this one. You want to be kind of careful that this is not something you can do on a live database, because then you're going to have more events that you didn't include. And then we will actually add a trigger to the database that will update the counts in that table whenever an event is inserted. So to actually implement this trigger, we need to do an upsert. And well, I'm giving you the example here of how to do an upsert pre-Postgres 9.5. In 9.5, there will be a very nice syntax for doing inserts, and if the row already exists, update. But in pre-9.5, this syntax didn't exist. So the way you would do upsert is more or less like this. If there is already a row for a date, just increase the count, increase the value by 1. If no row can be found, try to do an insert. Now, between the update and the insert, someone else might have already inserted a row. In that case, this second insert will fail, and we'll go back to doing the update, and then that should succeed. And this is more or less it's pretty similar to how upsert actually works in 9.5, but like the syntax is a bit nicer now. Okay, so if we put this into a function, then we can call that function in a trigger. And notice that I've added some file names to help you find these examples in the repository. So creating the triggers, so after any insert on data, for each row, we'll execute the procedure update daily aggregates and add 1 to the cached aggregate or the cached count. So having done that, let's run our script. So you could try this yourself and load some data, and then something terrible happens. Actually, where before we were getting 1,400 rows per second, now we're down to a few hundred. It varies widely. Actually, if you run this, what you'll probably see is that one process will still be getting 1,400, 1,500 rows per second, or maybe a bit less, and then all the other ones will have worse performance. And so why is that? What's happening here? Because the update or inserts on the cache table, they shouldn't actually be that expensive. But actually, whenever an insert happens on the data table, and there's a lot of inserts to do, when they all update the same row, basically, and that means that they all end up taking a lock on that row for that one date. Even worse, they're probably all updating the same day, like today's date. So basically, the one process that keeps getting the lock will see good performance, and everyone else will just be waiting for that process. And then the other part of this, what's bad about this, is in Postgres, if you do an update, because of the way the MVCC, the multi-version concurrency control works, you don't actually update the value on disk or overwrite the value on disk. Rather, you take the new value of the row and you append it to the table, and you mark the old one as no longer visible. So when this happens thousands of times per second, you're going to build up a lot of what's called bloat, all these rows that have been updated but are still sitting somewhere in the table. And so this costs a lot of disk space, makes queries slower, and eventually needs to be auto-vacuumed, and auto-vacuum can slow things down. So it's not something you want to do. So instead, let's try a different approach. And this is kind of building an incremental materialized view on top of PostgreSQL using just SQL, basically. And so the way this will work is we're going to have a queue of changes. So we keep a cached table of cached aggregates, and then we're going to have a queue of changes to those aggregates. And whenever we insert something into the data table, we insert the change to the aggregate into the queue. And inserts don't need a lock, so we can do that pretty quickly. Now, of course, our queue size will grow and grow and grow, and eventually, scanning the whole queue will become a lot of work. So eventually, we'll need to merge all the stuff in the queue into the cache table. But we don't have to do that very often, or at least not on every event. And if we do this, we can also easily support deletes and updates. Which for events, that's not such a natural thing. Like events don't unhappen, but if you think of bookings, of course, bookings can get deleted. So if you look at the number of bookings on a particular day, if a booking gets canceled, that number should go down. Or if that booking gets updated, it's like one date should go down and another date should go up. So we can support that just by, in case of delete, doing pushing a -1 into the queue, and an update we can push 1 + 1 and 1 - 1 into the queue. So we can support these different changes to the data table. And then if having these two tables now, like we have one cache table and one queue table, we need to somehow combine those results. So the query that the dashboard will run will look something like this, where we take a union of those two tables and then sum all the values. So we sum, let's say, 211 with +1, -1, and whatever else is in the queue, and grouping it again by date. And of course, to make this sort of nice and transparent, you can create a view, an actual view, and not a materialized view. And where the cache part is just going to be static and the queue is going to be growing. Okay, so to set this up, we'll create a queue table, and this is going to have like a date. And by the way, all these examples, they also extend to having many more groupings. So you can group by date, by type, and by repository, for example. So you can get, for a particular repository on a particular day, how many events of this type occurred. And then you probably want to create an index on this queue just to make queries that search for a particular date range fast. And it mustn't be a unique index, because we're going to have the same item occur, or the same date occur many times. And so whenever we now do an insert into the data table, we insert into the queue as well. So instead of doing the upsert function, now we'll have a function that looks something like this. And we also want to support update or delete. So when we get an insert, we actually will insert into the queue, taking the date from the insert, and just we're adding a +1 or actually a 1 into the queue. And for example, when we do delete, we'll add a -1 into the queue for that date. Now, what we've done here, and this is not necessarily the best way to do it, but it has some benefits. At this point, we check, well, 1 in every 10,000 times on average, with some random probability, we'll actually flush the queue. And so what this does is it keeps so without having to keep any state on how big the queue actually is, it keeps the queue within a certain size on average, like between 0 and 10,000 more or less. And then we'll call the function to flush, and that does mean that once in a while an insert into the data table will take slightly more time, because it actually also does the flush work. So another way is to do this in kind of a background process where you do it periodically. But the nice thing about doing it here is that it protects against sudden bursts. Like if you suddenly get 100,000 events, you'll actually start flushing much more quickly. And the full example of this function you can find in the repository as well. So the flushing into the queuing table or flushing the queuing table into the cached aggregates table is a bit involved because we need to do a couple of things at the same time. One is we need to sum up all the values in the queue for each date. Then we need to, because we still have the upsert problem, we need to check which values already exist in the cache table. And then, and by the way, if you're even on 9.5, it's probably quicker to do it this way than to do actual upserts. Then we need to update values that already have a row in the cached aggregates table, and insert dates that don't have a row yet, and delete all the values that were in the queue. And we need to do all of this on the same kind of state, same snapshot of the database. So a practical way of doing that is actually to do it in a single statement, such that we make sure that the stuff that we use, that we aggregate and put into the cache table, is the same stuff we delete, and we don't end up deleting more. So using CTEs can be a practical way of achieving that. So to zoom into all these parts, they're all reasonably straightforward. So we have this queue table, and we do a query on it, which groups by date and then sums up all the diffs in that in the queue. And then we need to, this just adds one column to that result, which says whether the date already exists in the cache table, or here called the materialized table. Now, having that information, we can start doing the updates. We can increase all the values for rows that do exist, and for rows that don't exist, we can do an insert into the cache table. And then finally, we can delete the old data from the queue and finish the query. Basically, we need to call these, we need to use these CTEs somehow, so we can just print a query that shows the number of updates, inserts, and deletes. And that will basically clear out the whole table. Or by the time this is done, there could be new items in the queue, but that's fine. Our view will always be up to date. So one thing to add if you set something like this up, it's probably not useful to do two flushes at the same time because they're just going to interfere. So you want to put a lock on there, and you can use an advisory lock, which, if it cannot get the lock, just returns, because at this point you're happy that there's already a flush going on, so you don't need to do anything. So this can happen because it's just random, basically. So the last step then is to add, or the second last step, is to add a trigger to the table. So now we can actually do inserts, updates, and deletes. And then whenever there's one of those queries, we append to the queue table, and periodically that calls the flush function. So the last step is actually to create the view that does the summing of the cache table and the queue table. And well, we've shown this query before, and the dashboard will just be querying the data daily counts view, which will in real time show like the accurate number of events on that day, because the queue gets updated whenever the data table gets updated. So it will, without doing any locking on the cache table, it will update the view in real time, essentially. So now when we run a query on this view, it actually does slightly more work than it did before. So I mean, these queries are all so fast that it's barely noticeable. But it does need to add up all the items in the queue, but still, there's only going to be a couple of thousand, and it's a very small table. There's not many columns, so it's really only a few kilobytes that it needs to process. And this gives you the number of events per day. And now if you load data, we see, well, it's not as fast as it was at the start. I mean, you're going to notice that you're doing slightly more work, but it's not disastrously like the previous approach, where we which was 10 times lower or even worse. It's actually pretty similar to the original data loading speed. So now we can support fast ingestion of data, have a view that's actually real time, and have fast queries on that view. So that's a pretty nice combination. Now, but we actually want more. Very often you have like different granularities of time that you want to look at in this dashboard. We saw weeks and days at the start. Often you have something like, show me an hourly graph or even like a 1-minute graph, and then might want to track it over the last week or the last year. And what's interesting is that you don't actually need to create separate triggers on the data table, which makes ingestion more expensive. Rather, whenever something is changed in the hourly table, you can just add it to the queue in the daily table. And whenever something is changed in the daily cache table, you can add it to the queue in the monthly cache table. And you might think, well, then isn't the daily table behind? Well, yes, but actually in the daily view, you can include both the cache table, the daily queue, and also the hourly queue to include all the recent changes that have not been flushed into the hourly queue yet. So you can, as long as you include all those parts, you will still get an accurate real-time view of your aggregate. And this saves a lot of, this keeps ingestion a lot faster. It saves a lot of work by having these cascading views. But of course, this is a pain to set up. Given like all the code that we already wrote, you probably don't want to do this completely manually. So we actually wrote a little tool that you'll find in this GitHub repository, where and it's an example. It's like I wouldn't recommend using it in production, but just to see how you could write something like that. And this is purely in SQL. This creates a cascaded rollup where if you call this function, so it uses the data table and creates a rollup called data by type, which is just all the data grouped by time, like hour, day, or month, and by type. So for every day, you can see how many events of a certain types were there. And well, here with ag count, you specify which statistic you want to compute. So in this case, you want to take a count star, and we'll call that column count star. So just the number of events. A more interesting example is breaking it down by type and by repository. So for each day, for each repository, we can look at how many events were there of each type. And actually, in this case, we're not going to look at the number of events because we can also do other aggregates. In this case, we're going to look at the number of commits, and in the GitHub data format, the number of commits is given by distinct size in the payload field. And so this will create a roll-up or an aggregate that will actually, that's the one we can use for implementing the dashboard that we saw at the start, namely number of commits per day. And then, well, there we had number of commits per week. Actually, we could change this to be week. And what this generates is it generates the queue tables for hourly, daily, and monthly. It creates the sort of materialized tables or the cache tables. And then the data table will have a trigger that inserts into the hourly queue. And in the hourly cache table has a trigger that inserts into the daily queue, etc. And then there is the views. And so for example, the daily view combines the materialized table with the daily queue and then the hourly queue to get a complete real-time view of the aggregates. So if we query these views, and here I could show you the database. I have a little test set up where I loaded 1 month of data. So here you can see the data table, and it's it follows the format we saw, and there's a couple of triggers on it actually. So one is, does the random kind of check, so check if once every 10,000 times on average, call the flush function, and the other one is the one that appends to the queue. And we can, for example, look at what is exactly in the queue by looking at, right, so you can see there's a lot of, I should probably run limit 10. There's a lot of, there's only push events actually have commits. So here you can see, well, this push event had one commit, this one had one commit. Maybe if we do, okay, so these are all increasing the value of the number of commits on this repository on that hour by 1. And then in the end, I can run something. Oh, let me actually show the view. The view is kind of interesting. The view, as I said, combines the materialized table, with the hourly queue and the daily queue and sums them all up. So if I query that view using this query, where I look for the Postgres repository, I want all the push events and give me the number of events by day. It gives me that, and this query runs in about 1.4 milliseconds. And I can also start loading some new data here, and this at some point will give me like the number of rows per second that it was able to insert. Right, so actually doing 1,500, close to what we actually had originally. And I can see, well, it's already been updated with actually the new data from February 6th in kind of real time. So we have those properties. I can also do the, I didn't actually create an explicit weekly roll-up here. I could actually run a query where I just extract, I basically aggregate the daily aggregates into a weekly aggregate, right? I don't always need to make an explicit aggregate. So this could save space if I don't want to have a weekly one. I can just generate it, using SQL. And this kind of fills in like these are the two queries that we kind of want to make for building our interactive dashboard. We can see that we have fast ingestion and we have fast queries on this end, and they get updated in real time. So that's what we wanted to achieve. And then here, this is one kind of an example query that we added. That turns out most of the work on Postgres, or most of the commits, seem to be done on Sundays, which is interesting. In terms of size, so the data size here in this example was about 19 gigabyte. I added a few more days, so probably about 20 gigabyte. And the aggregates also turn out to be, still quite big. So you want to make sure you put indexes on them, especially hourly by type, by repository. There's a lot of repository, 20 different types, for 24 hours a day. So there's a multiplying factor there. So this adds up to be quite big. So very often you might at some point want to remove older, hourly data because you don't really care maybe what precisely happened at 2 p.m. at December 22nd, 2014. So you typically want to throw like older data away and also throw away older raw data. Now with the script that is in the repository, this will actually not work because that will actually trigger the trigger basically and append minus one to the queue. So you can't actually delete the old data using that script. So it's like an example. Don't use it in production. So other improvements for those scripts, like having the flushing in an insert will make one in every 10,000 insert quite slow. So you might not want that. So if you put it into the flushing into the background worker, then you could actually have lower latencies for your writes. And yeah, if you had the if you didn't have the delete trigger, you could actually save space by throwing away older data. So this works for aggregates that can be incrementally computed. Not every aggregate is suitable for that. The ones that are is definitely count, we showed you, and some can also be incrementally updated, like you can just keep adding the number of commits to a sum as we showed. For average, you can't just keep averaging the averages, so in that case, make sure you have a sum. Just instead of storing an average, store the sum and the count, and then in the view you can sum the sums and divide it by the sum of the counts to get the overall average. There are also some specialized data structures for basically doing incrementally computed distinct counts, particularly the hyperlog log, and there's a very nice Postgres extension for using hyperlog log, which basically gives you an estimate of the number of distinct items. Let's say you want to count the number of distinct users that committed or distinct repositories that had events. Hyperlog log can keep track of this incrementally, and it won't give you an accurate result, but it will give you an approximation that's within a few % of the actual value, which for generating graphs is often good enough. Similarly, there's top n if you want to keep track of like which are the top 10 items with the most events, for example, like the top 10 visitors or top 10 committers. There's also approximate solution for that, like count min sketch. There's also some Postgres extensions that do that. So the final part, I want to show some or discuss some considerations if you want to scale this out. Like, as I said, the aggregates can be quite big. The amount of work involved, like the amount of data, can be quite big. And it can sometimes be attractive to actually partition your database across multiple nodes. And you can use extensions like pgshard or CitusDB to make that kind of transparent. So CitusDB has the notion of a distributed table and then can run queries in parallel on that distributed table. But you have to make decisions when you partition your data. You have to make decisions about how you're going to partition it. One way is to hash partition it. So let's say you pick one partition key, one partition column, like the repository name, and then each, when a new item comes in, CitusDB will calculate a hash of the value in the partition column of the repository name, and then based on that, it goes to a particular shard. And you can actually use the technique we just discussed of having these incrementally updated aggregates with queues on each shard, and a shard in CitusDB is just a regular Postgres table. But you can only do it as long as both the data and the aggregations that you want to calculate are partitioned by the same key, such that all the data for a particular set of repositories is on one node, and other repositories are on another node, etc. So you can do this if your aggregations are also have partitioned by the repository name, and so the repository name has to be one of the fields that you group by in that case. You can also use range partitioning. A very common use case is to range partition a table by time, such that new data can be loaded in bulk. And you can use this technique on basically whatever the latest shard is. So you keep cached aggregates for all the older data, and then you keep incrementally update the aggregate for the latest ones. But then if you want to do a roll-up over a month, then this this will require pooling data from different machines together, and that can get very complicated. So there's which partitioning scheme you pick kind of restricts you what you can do in terms of calculating aggregates, or how easy it is to calculate certain aggregates. Like if your data is dispersed everywhere, then calculating the number of events per month can certainly be quite difficult. Then these databases also give you kind of an alternative, which is to actually just query the data in real time just query the data in parallel, which even if you query the raw data, can give you close to real-time results if you have enough horsepower behind it. So this is something you can do with CitusDB, and the next version of CitusDB will be released as a regular Postgres extension that you can install on Postgres 9.5 or 9.4, and will be released early next year, open source. And in some cases, you can query the raw data. In other cases, some users of CitusDB, like Cloudflare, they actually create tables containing pre-aggregated results and then query those tables in parallel. So it gives you different options, but like you need to think about how you partition your data and how are you going to query it. Also, when you're doing a distributed query, there's some considerations like, well, if I run a group by repository name and my data is partitioned by repository, and let's say I want to get the top 10 repositories by number of commits, then I can just send that, give me the top 10 from each partition, from each shard, and construct a big list and sort that and take the top 10 from the list. So that's very easy. That's very nicely parallelizable. But if you actually group by another column that's not the partition column, you will actually have to, when you're running the distributed query, you will have the query planner and executor will have to pull a lot of information into one place to actually add it up. Like, we'll get some information about how many events there were for this repository from shard A, and then another bunch of information from shard B, and we need to add those together. So then certainly there's a lot more network traffic. So when you're using distributed tables, you need to think a bit about, like, how is my data partitioned versus how do I actually query it. But a way to avoid this, if you actually just store aggregates in the distributed table, then clearly any query can just be pushed down directly. So final notes, I brought up the repository a couple of times. If you didn't write it down, you can do so now, or look at the slides later after the webinar. We'll put them on the blog post as well. So with that, over to Terry, are there any questions?
Thanks, Marco. Once again, if you have any questions, please enter them in the questions panel in the GoToWebinar control panel. Marco, could you please just give a quick overview of the difference between this and the tutorial that you presented at the PGConf Silicon Valley?
Yeah, I mean, there was, well, the one difference was time, so we spent a bit more time having people run through exercises, and like we gave everyone an EC2 instance to connect to and actually run these files. So most of the content is similar. In that case, we also had a section on hyperlog log, which we might publish something about in the future as well. But the only thing missing was actually the hyperlog log part, and otherwise you can run the exercises, the same exercises that we did in the tutorial. Okay,
very good. And are there any other resources that you would point to that might be good sources of information on this topic?
That's a great question. I would say contact us. We like this is kind of the kind of use cases that Citus Data deals with a lot, and it's not an easy problem. So you're gonna have to. There's not like one solution out there that fits everyone's need. Certainly, like some basic things is like the PostgreSQL HLL extension that I would recommend looking at if you are interested in distinct counts. And it's like the documentation is quite good, and the extension itself is also quite good, and it helps you do things. If I want to estimate the number of unique visitors on a day, which is a very common use case, definitely check out the PostgreSQL HLL extension. Yeah, other than that, like I think there is some documentation out there on like general techniques for building these views. So we can maybe include some links in the follow-up blog post.
Okay, very good. If we don't have any more questions, we'll wrap it up for today. Thank you, Marco, and thank you everyone for attending today. We will send out a link to the video, to the recording of this webinar within the next 24 hours or so. Thank you. Have a good day.
Thanks.